Chapter 16, slides 11 through 16. Okay, our last two considerations when we're doing a Diels-Alder reaction involve the facial attack of the dienophile, like the top face versus the bottom face. And then lastly, what the stereochemical outcomes are at positions that are prochiral. What's prochiral? Well, I mean, if you look at the Diels-Alder reaction that I'm showing you here, notice that there could possibly be stereocenters, right? Chiral carbon centers where you have four distinctly different groups on a tetrahedral carbon after all is said and done. So are you going to make the R or are you going to make the S? What goes into figuring this out? Well, the first thing I'd like to do is number 5, which is pick a face. As I mentioned, the transition state for a Diels-Alder is set up in a boat configuration. So it's good practice, just like it is with a chair, to know how to draw a boat. And then you can see that the dotted lines represent where the new bonds are going to form. Now, picking a face means, is the dienophile going to come in from the bottom? Or is it going to come in from the top? Since this class does not cover facial selectivity, which side is going to be preferred, just get used to drawing it one way. And the way that I think is easiest to draw it, for whatever reason, I don't know why, when you have a choice and you can do it either way, just choose it from the bottom. Can it come in from the top? Absolutely. But we're going to just use the boat transition state where the dienophile approaches from the bottom in a boat conformation, and then figure out what it is that we get. We can figure out the other stereoisomer by flipping all the centers after we're done. So just get used to drawing it one way. So I guess my answer to number 5, pick a face, pick the bottom face arbitrarily just because it's easier to draw, and go from there. It's another class entirely trying to figure out whether the top face or the bottom face would be preferred. In most of the cases that we're doing, you're actually going to get both top and bottom side attack. Again, remember that these systems are very flat. Each of these carbons in the diene and the dienophile are trigonal planar. And so it's a very flat system approaching a flat system. So approach from either face will be observed. Okay, so the last, number 6, the last thing we have to think about is when we draw the boat transition state, and arbitrarily we've chosen to come in from the bottom with the dienophile, there are effects of this choice. So if we had hydrogens on the inside of the mouth, the teeth, and some other groups on the outside, this will end up having an effect on the overall stereochemical outcome. Now, what do I mean by that? Well, take a look at this first diene. This diene is already in its Pac-Man conformation, right? It's in its S-cis conformation. And what you'll notice is that there is a very specific geometry of the double bonds. If I were to point to the top double bond and ask you if it was a cis or trans double bond, you'd say it's trans. If I pointed to the bottom double bond, you'd tell me it's also trans. And what this means is that there's a very set configuration around that double bond. Inside the double bond are the hydrogens. I'm going to represent them as round white circles. Now, in a Diels-Alder reaction, the reaction proceeds such that the inner teeth, as I'm going to call them, right, the white circles in this case, will rotate disrotatory. Now, if you ever wanted to learn more about what this means and how you can predict disrotatory versus the opposite called conrotatory, you'd have to probably take an advanced organic course. Disrotatory means that the rotation of each carbon is in opposite directions. One's going to go clockwise, one's going to go counterclockwise. What does that mean for us? Well, it means that the effect is that Pac-Man's teeth, those two white ones in the middle, if the approach of the dienophile is from the bottom, which I told you to pick a face, any face, think of it as kicking the teeth, the teeth get knocked up. So if the dienophile approaches from the bottom, the inner two teeth get knocked up. Notice that on the carbons that I'm indicating, those two hydrogens are up. By rotation, the methyls get tweaked back or down. So you'll notice that the configuration of these two stereocenters is such that the methyls are on the same side back and the hydrogens are on the same side front. Now, what's important to recognize is that I picked a face, any face. Had I chosen to pick the top face, both of those teeth inside the mouth would have gotten knocked down. So I also will see the hydrogens both down and the methyls both up. Both of these products are achievable, and you're probably going to get a mixture of both of these. Now, is this truly a mixture of two different compounds? I don't know, right? Is this a chiral molecule to begin with? Yes, it has two stereocenters. But as we know, there is a plane of symmetry internally. So this is actually a meso compound. Therefore, it is not chiral. And although I could have come in from the top, coming in from the top actually just gives me the same molecule. Rotate that molecule around and you'll see that they are indeed the same. So for this particular Diels-Alder reaction, you'll only get one major isomer. And the relationship between the methyls is that they're both syn or cis on the ring to one another. Okay, how about the next one? Notice that we have our Pac-Man already drawn. And if I were to ask you about the double bond here, you'd tell me, oh, it's trans. And if I asked you about the double bond on the bottom, you would tell me it's cis. So this is a different starting material than the one I started with above. Now, let's evaluate what's inside the mouth and what's outside the mouth. Outside the mouth, we have a methyl group and a hydrogen. I'm going to draw in that hydrogen. I'm not going to assume it. Inside the mouth, we have a methyl and a hydrogen. So if I pick a face, bottom face, from the bottom, I knock the teeth up. That means the hydrogen for the top carbon after the Diels-Alder is knocked up, and the tooth at the bottom is the methyl. So the methyl on the bottom one gets knocked up. Notice that this is a different orientation than the above. This is not a meso compound. And so there are two molecules made. If I attacked from the bottom, you get the one shown. If I attacked from the top, I get the enantiomer. Since these are not meso compounds, they are chiral, and I get a mixture of enantiomers in this case. Notice that the relationship between the methyl groups is trans across the ring. All right, we can model this, and I can show you the movement of the inside of the teeth as the approach of the dienophile comes in from the bottom. So if you just imagine that my body is the cup shape of the diene, and my hands represent the inside teeth and the outside groups, and you'll see that a disrotatory rotation as the approach of the dienophile comes in, one turns clockwise, one turns counterclockwise. You see that the inner teeth move together up or together down. I have some practice here so that you can have a go at more Diels-Alder reactions, but I really wanted to work on one from start to finish with you, putting it all together. So let's do this case. This is a tough problem, and it kind of encompasses everything that you need to know about a Diels-Alder. Step 1, find your diene and your dienophile. All right, 1, 2, 3, 4, 5, 6. Let's highlight. There's my diene, 1, 2, 3, 4, 5, and 6. Step 2, do I have the S-cis Pac-Man configuration? I do, because it's locked in as a ring. All right, perfect. Let's put these together. I'm going to use the boat configuration to set things up. And use a pencil because you can erase things as you go along. 1, 2, the methyl, 3, 4. Now, I gotta figure out, maybe I should skip to the electronics right now and figure out which way that ester, is it gonna be as indicated, or do I have to move things around? So let's think about the plus and the minus. The best position for a positive charge, given the fact that I have this electron donating group, methyl, is carbon 2. That would be the place where the most stable partial positive charge would be. So by conjugation, extrapolation, I can figure out the electronics around the diene. And given the withdrawing group, I know that carbonyl carbons are partially positive, so that makes carbon 5 partially positive, right? So partially negative, partially positive, and by extrapolation, partially negative, partially positive. So I want carbon 5 to be associated with carbon 1. I don't want it to be with 4. 4 is already positive, so I need to make it so that carbon 5 and 6 align just like so. Okay, now I have carbon 6 is the one that has the ester off of it. And I need to put that ester endo. Right? Because I know that the p orbitals of this ester are going to have secondary orbital overlap with the back lobe. Okay, so I've got my endo configuration. Carbon 6 has a hydrogen, has a hydrogen, has a hydrogen. So I just like to fill those in. And then let's look, do I have to worry? Oh yes, I've got carbon 4 and carbon 1 share this inner tooth. It shares one tooth on the inside, and on the outside are my hydrogens. So that inner tooth, right, is going to get knocked up if I've chosen to come in from the bottom face using the dienophile. Now we push our electrons. You can see that the electrons get pushed to make the new bonds. I have my new double bond between 2 and 3. 2 still has a methyl group off of it. 4, 6, 5. These are all still hydrogens. Remember, the ester was tucked underneath the ring. And then I know that the tooth got knocked up. So it's like a bicyclo-tented system. You could have also written it like so. Notice that if I were to be looking at it from the top face, you could see that the tented bicyclo system is coming at me. You can also see that the ester on carbon 6 over here, carbon 6, has the ester going down and away from you. So the relationship between the tented up part of the ring and the ester, they're trans to one another. So we have to reflect that in our product. Had I chosen endo, but from the top face, the other product would have been trans again, but the opposite enantiomer. This is a hard problem, but it encompasses all parts to a Diels-Alder reaction. And you can see the very methodical way in which you can go about solving these problems. I'm going to leave this one with you to solve. This is another tough problem. I'd like you to follow the same profile that I showed you in the previous one to see if you can solve the product distribution of this Diels-Alder reaction. Now, as I mentioned, as I started back at the beginning of Diels-Alder, this is a biomimetic pathway. This is a way that nature can very easily, using the light of the sun, to construct six-membered rings when you have a foundation of a double bond, maybe a terpene system. You can actually put these together. We also can utilize this chemistry in the laboratory, in a beaker. And so here is a precursor. This is a key synthetic step in making the functionalized skeleton of lovastatin, which is a drug. And it's a statin drug. And what you'll notice is that it takes many steps for scientists to make this long chain. And you have to have these double bonds made right here between 2 and 3 and 4 and 5, and they have to have a trans configuration, each one of them. And then the diene over at 10 and 11, notice that it has its electron withdrawing group attached. That has to have a trans configuration as well. And when you heat this molecule up, you take this one molecule, you've got the diene 2, 3, 4, 5, and the dienophile 10 and 11. This does an intramolecular Diels-Alder. And what you can see is I've redrawn over here this molecule. I've bent it into the S-cis configuration and drawn the 11-10 dienophile close enough for the reaction. And in one pot with just some heat, you get 2 new carbon bonds in one pot, one step, giving you the bicyclo system, the 6,6 bicyclo system, on its way to lovastatin. Pretty slick, elegant chemistry. Well, that's about it. This is just where now it's your turn to start practicing the protocol of a Diels-Alder reaction. And I know it's a lot to take in, so this is one of my favorite jokes. What does a student typically say when they see the Diels-Alder question on the exam? I'm sure you can see it now. I'm dying. I hope that's not how you feel when you get to the exam, and hope you can crush these Diels-Alder reactions. They're kind of fun once you get into the swing of it, but you just need to understand the method. But ultimately, what I'm hoping that you understand and appreciate is that this is one of the first biomimetic pathways you've looked at, and how beautiful it is, how you can take something that's electron rich with the double bonds and electron poor double bond, and they come together with just heat or light, and you make your beautiful 6-membered ring.